Okay, so here's a family of 5 periodic polygons, Poncelet polygons, interscribed between two non-concentric ellipses, which are not axis aligned. So you can see here that the caustic inner ellipse is both non-concentric. Its center is right here, the center of the outer ellipse is right here, and its axes are obviously tilted with respect to the axis of the outer one. Okay, now before I started this video, I did some numerical optimization to find such a, say, general position pair of nested ellipses that would admit a family, a Poncelet family of 5 periodics. There's this thing called the Cayley condition. It's a very nonlinear equation you must solve, but you can do this numerically, and you get, for this example here, that is going to serve us well for the purposes of this video. So let's watch this family some more. You can see that its vertices are labeled P1, P2, P3, P4, P5. Every segment, as it's always the case for Poncelet, is tangent to this inner ellipse, this caustic, and every vertex is incident on the outer ellipse, or lies on the outer ellipse. Okay, now I want to define 5 diagonals. Let's go ahead and define 5 diagonals. So I think I can do this. Yes. All right. Now, how am I going to define these 5 diagonals? I'm going to start from a base vertex. In this case here, it's P1. And I'm going to connect the base vertex to P4 and P3. Okay? So how do I determine who is P3 and P4? I start from my base vertex. I'm going to walk counterclockwise 2 steps, and I'm going to find the other endpoint of this first diagonal. And I'm going to walk another step and find this other endpoint here, P4, and I have my first 2 diagonals. Okay. Now I'm going to define a third diagonal that is connecting, in this case, P2 to P5. How do I find its endpoints with respect to P1? I'm going to walk 1 step counterclockwise and find this endpoint of this red diagonal, and I'm going to walk 1 step clockwise, and I'm going to find the other endpoint. Now I have 4 points here. These 3 diagonals will define 4 points of interest to me. Okay, the first 2 points are the endpoints of this third diagonal. So they're marked here. Let's see if I move this a bit, we can see it better. They're marked A and D. Okay, they're superposed on P2 and P5. A and D. Now the intersections of this third diagonal with the first 2 diagonals are labeled B and C. I can change the labeling order so that they are sort of alphabetical. So now we have A, B, C, and D. Okay. Now what's really germane to this video is the fact that given 4 points that are collinear, there's a classical quantity that you can compute known as the cross ratio. Okay, so this video is about cross-ratio invariants over Poncelet N-Periodics. So if I take 4 points, so collinear, A, B, C, D, by definition, the cross ratio of these 4 points is simply the distance AC times the distance BD divided by the distance AD times the distance BC. So this is a really well-known calculation. I'm going to leave a link in the description. But I can now calculate and report up here what this cross ratio is. So I'm reporting it up here. CR1 cross ratio of this construction with respect to P1 is 1.311454. Now let's animate this family and let's watch what's happening to this cross ratio. Okay, as I keep my construction as specified, the 3 diagonals move around, as you can see, and it would be interesting for us to find out how B is moving, how C is moving, if they're ellipses or not, etc., etc. But lo and behold, that cross ratio AB, CD is not constant. Right away, you notice something quite curious is happening. Imagine that I would repeat this construction that is now anchored on P1, and I would repeat this construction to make it be anchored on P2. So I'm going to use the same rules, okay? 2 rays leaving from my anchor vertex, my base vertex, and then 1 cross diagonal. Okay, so let's go ahead and see it as I cycle this over to P2. It's the same construction. The only difference is that I'm now starting it from P2. You can see here that there's 2 diagonals leaving P2, and there's a cross diagonal connecting the neighboring vertices, the vertices that are neighboring P2. Okay. Now I can also report the second cross ratio with respect to P2, and I get a different number. I get 1.45. This number is variable. Okay. But let's just cycle. I'm on P2 now, 1.659. Let's go back to P1. I get a different number, 1.3485, when my anchor is P1. Let's go to anchor P2, as we just did. Let's go to anchor P3. Now I'm starting here from P3, 2 diagonals, and I'm yet generating a third cross ratio, distinct cross ratio. Let's now anchor it on P4, over here, 2 diagonals leaving P4. I get a different number. Okay, and finally, because this is a phi periodic, let's go to P5. Okay, so I get yet 2.33. So these 5 cross ratios so obtained using the exact same construction, and very importantly, the exact same ordering, A, B, C, D. When I compute the cross ratio of these 4 points ordered in this way, I'm going to get, with respect to each base vertex, a different value. Okay, so let's go back to 1. Let's make our base P1 again as we started. Okay, here's P1, 2 diagonals leaving from P1. Now imagine in your head that we have now the 5 computed cross ratios with respect to each one of those vertices. What this number over here is showing is that over the family, the product of those cross ratios, those 5 distinct cross ratios, is invariant over this quite asymmetric phi periodic Poncelet family. Okay, you can see also that the sum of those cross ratios is varying. Okay, now I'm going to leave a link in the description about cross ratios, but if you're given 4 points, there's 24 ways of ordering 4 points. Okay, if you take all combinations of A, B, C, D, there's 24 ways to order them. Yet there's only 6 of those 24 ways, or there's like 6 classes of 4 orderings that produce the exact same cross ratio value. And all those 6 cross ratio values are related in well-known ways, and you'll see it on the link in the description. Okay, now I want to choose a different ordering for these vertices here. So now they are A, B, C, D. We saw that under this ordering, we're getting invariant product of the 5 cross ratios in the family. Each one of them is variable, okay, but their product is invariant. Let's now choose a different ordering. I'm on ordering 3, and there's 6 possible ones. Let's choose ordering number 1. So instead of A, B, C, D, I'm going to do A, C, B, D. Recall that the cross ratio is always computed in a sort of a crisscrossing way. You always take the first and third point, that distance, times the second and fourth point, distance, and then you divide by the first and fourth distance times the second and third distance. So when you do these reorderings here, the result is going to be different. Okay? When we actually choose this particular ordering now, A, C, B, D, let's watch what happens. I continue to have a different constant product and of cross ratios, and my sum is still varying. Let's choose a second ordering here. A, D, B, C. Let's watch what happens. Okay, so now a miracle happens. For this particular ordering, A, D, B, C. Okay, under this construction, I'm going to repeat this construction. Let's go to second vertex here. So I'm repeating the construction with respect to P2. So I have again A, D, B, C as I traverse across, right, with respect to P2. Let's look at it on P3. Let's make P3 be the base vertex. A, D, B, C. Okay, so when I do this and I compute either the sum of the 5 cross ratios or the product of the 5 cross ratios, and that's very difficult to say, you can see here experimentally or numerically that for this particular choice, very special choice, I get this really interesting observation whereby both the sum of the cross ratios and the product of the cross ratios is conserved. I don't know if this is obvious, if this stems from some basic geometry in Poncelet, but it's pretty interesting nonetheless. Okay, now let's look at another family here. I want to look at 5 periodics now, so let's turn off these guys, and I want to look at 5 periodics that are self-intersecting. Okay, so let's scale this guy a bit down. Okay, so here we have an outer ellipse and an inner ellipse, and a family of so-called pentagram 5 periodics. So these are self-intersected 5 gons that are interscribed between these two ellipses. Obviously, the caustic is not concentric and it's not axis aligned. Okay, now let's go ahead and repeat our construction here. I want to take a vertex P1. I want to draw 2 rays, and there's exactly 2 segments incident on P1. And I want to find across another segment that cuts across those 2, right? So let's go ahead and do that. I believe it's like that. Right. And here you have to actually squint a little bit to see this, because the segments are themselves, the diagonals are themselves segments of the trajectory. So you can see here that I have a dashed red that is going over P1 to P2, and I have a dashed red that is going over from P1 to P5. Okay, and my cross segment is now connecting P3 and P4. For this particular case, the indexing to get the 2 outward from P1 and one that cuts across is slightly different, but it's still the same idea, right? The one that cuts across is P3 is here clockwise from P1, and P4 is counterclockwise 1 step from P1. Then you have P2 and P5, and you get this kind of a construction here. Now, what is my ordering right now is A, C, B, D, some particular ordering. And let's watch what's happening to my cross ratio for that particular ACBD segment, or ACBD. It's not constant. The sum of those cross ratios is not constant, but the product is constant. Okay, let's choose a different assignment of those 4 collinear points. Let's choose the assignment ADBC, and let's see what happens. Okay, so for this particular ordering of the 4 collinears, both the sum and the product are being conserved. Now I want you to take a look at these 2 numbers. Okay, product is 18.865 blah blah blah, and the sum is 15.865 blah blah blah. It looks like the product is exactly 3 integral units above the sum. Okay, was this the case on the previous situation when they did not? This was not a self-intersecting, not a self-intersecting 5 periodic. Let's check. I went back to that first example. Here's a particular ordering for non-intersecting 5 periodic. It's the exact same one that produced the 2 invariances of both sum and product. And you can see here, lo and behold, they are both invariant, and the product is for some reason 3 integral units above the sum. Okay, of course I don't understand why that is right now. Okay, let's move on. Let's go to the n equals 6 case. So let's do an n equals 6 case, and let's first of all look at it. Let's look at this family. It's an n equals 6, interscribed between 2 non-concentric, non-axis aligned ellipses, nested ellipses, 6 vertices. Let's make this guy be a bit more visible. So here's my P1, P2, P3, P4, P5, P6, 6 periodic. Okay, now let's go ahead and define. Now we're going to have more choices for your diagonals. Okay, and we're going to go over them. It's a pretty interesting set of observations. Let's find a first assignment of diagonals. I'm going to start from my point P1. Recall that on the n equals 5, I didn't have a lot of choices for those 2 lines that are emanating from P1. So here I can choose. I have P3, P4, P5, right? I have these 3 choices here. Okay, but I'm going to choose for this particular set of diagonals P3 and P4. And for my cross diagonal, I'm going to choose P2, P6. Okay, now let's watch what happens under the cross ratio ordering A, B, C, D, default one. Okay, you can see here that the only conserved quantity is the product of cross ratios. Let's change that ordering to A, B, D, C. Let's see what happens. Still only the product is being conserved. Let's go to another ordering. Now I have A, C, B, D. Now something strange happens here. First of all, with this particular ordering, and I don't know why yet, the product of my cross ratios is 1. Is exactly 1. Are all my cross ratios 1? No, they're not. Here's one of the cross ratios, 1.012. Let's flip through them. Here's my second cross ratio with respect to P2, 0.45. Here's my third one, 2.1. So now when I say my third one, I'm starting from P3. I'm drawing those two diagonals using the same sort of ordering rule that I had in the original P1. And I have my crossbar here. Okay, and the ordering is A, C, B, D. Okay, so you can see here that the product of these 6 distinct cross ratios, varying distinct cross ratios, is 1. Okay, their sum is not conserved in this particular choice. Okay, let's go for the fourth ordering. So the fourth ordering of collinear points is A, C, D, B. I'm still at 1 here, and I still have varying sum of cross ratios. Okay, let's go to the fifth one. So now I have, there's 6 of them, right? 6 possible orderings. A, D, B, C. Okay. So now my product of cross ratio is constant, but it's not 1 anymore, and the sum is varying. Okay, let's go to the final one, 6th ordering. Again, nothing really amazing happening here. We're not able to, with this particular choice of diagonals, we're not able to stop both the sum and the product. Okay, but we were able to achieve via 2 of the orderings an interesting property where the product of cross ratios, for example on this one here, A, C, B, D, is exactly 1. Okay, so there's probably some really interesting symmetry here, and we should study this problem a little more to find out why that is. Okay. By the way, this result here, you can actually tweak the axes of. So let's tweak these axes here. Let's say of the caustic, so that the trajectory no longer closes. Okay. I'm going to tweak it a little bit. You can see here that the trajectory is not closing anymore. Okay, I'm sort of moved away by tweaking the b-axis of my caustic from that specific configuration where you get 6 periodics. Okay, so right now I don't have 6 periodics anymore. You can see that my trajectory doesn't close. So as I move P1, I don't close the trajectory. So if I continued on here, I would get something that never closes, right? I could continue this trajectory. But let's just focus on the n equals 6. Okay. This particular choice of diagonals, even for the trajectory that does not close, continues to produce a cross ratio, a product of cross ratios equals to 1. It's only on this case that I've seen this behavior. So if I make my base, for example, be P1, you can see here that P1 is not even a vertex of a closed n equals 6, and yet the product of the 6 constructions, okay, product of these 6 constructions from each one of the vertices, okay, here's P6, okay, continues to produce a product of cross ratios equals to 1. Okay, so let's go back to our closing n equals 6. We're restoring some sanity here. It was just a side note, pretty interesting. Let's go to another choice of 3 diagonals for n equals 6 non-self-intersected. Here's another choice. So now you can see that my cross diagonal is no longer P1. Let's reference this guy here to the first vertex to P1. Here's P1, and let's go back to the previous setup. In the previous setup, recall that my cross diagonal was between vertices that were directly neighboring P1. I have another choice here. I can make that cross diagonal be between P2 and 1 step over from the direct neighbor, so to P5. Okay, and I have again a construction with 2 diagonals emanating from P1 and 1 between P2 and P5, no longer between P2 and P6. Okay, now the same thing, I can report cross ratio with respect to P1 is this number here, 0.29. If I moved over to P2, okay, let's move over to P2. Now I'm sort of doing this with respect to P2. I get a different cross ratio. I can go move over to P3. I get a different cross ratio. So you can do this for all 6, and you can collect the sum of those cross ratios and the product of those cross ratios. So let's reference the one drawn on the screen back to P1. And let's go ahead and animate this guy with a particular choice of, and I want to do A, B, C, D, always to start with A, B, C, D combination for my cross ratio. Let's see what that accomplishes. So for this particular choice, A, B, C, D is not maintaining either the sum nor the product constant. Okay, let's do a second choice, A, B, D, C. What does that do? Now only the sum is being maintained invariant, and it's actually 4. Okay, go figure it. Number 4. Okay, and you can see that something else pretty interesting is happening here. Since D is the meet of two proper diagonals of this 6-gon, right? What's a proper diagonal? It's really connecting vertices that are opposite to each other in the counting of 6 vertices. So if you start P1, P2, what's the opposite, so the diametrically opposite vertex to P2? It's going to be 3 vertices forward, right? So you go 1, 2, 3. So this is P5 is diametrically opposite vertex to P2. And then in this choice of diagonals, we also have the P1, P4, and they meet at D. Because this is the meet of two proper diagonals, this point is going to be invariant over the family. Okay, the point is going to be stationary. What's really interesting here is that with this particular choice, I'm not managing to stop the product of cross ratios, but the sum of cross ratios is stuck at this beautiful number 4. Let's do that experiment we did before. I'm going to go ahead and tweak one of the axes, for example, the b-axis of the caustic, to open up this trajectory a little bit. So I'm opening it up right here. And let's see if either the sum or the product remains constant. So you see, the sum is no longer constant. Recall that in the previous case, we opened up the n equals 6 trajectory, and that product remained equal to 1. But here, we're not getting the same phenomenon, okay? So let's go back to a close n equals 6. Let's go back to the case where our sum was equal to 4, as you see it here. Okay. All right, let's make another choice here. So we have A, B, D, C. Let's choose A, C, B, D, our third cross-ratio vertex ordering choice. Now, in this particular case, only the product is being conserved. Let's go to the fourth. Okay, so on the fourth situation, the fourth choice of ordering, A, C, D, B, starting from P2, right? A, C, D, B. I'm managing to conserve or to stop or make invariant both the sum and the product of the cross ratios. Now here they're not related to each other by 3 integral units as they were before. Okay, but there could be some ratio or something interesting that needs to be studied here. Okay, so this could be some rational. So if you divide one by the other, you could get some rational number, but we'll study this later. Okay, so the important thing here is that we found an ordering for the cross diagonal such that both the sum and the product of the cross ratios are invariant. Let's try our fifth combination. In this fifth combination, the ordering is A, D, B, C, and now only the sum is stationary at 2.0. Okay, let's see if the sum remains stationary when we tweak the caustic. Let's tweak it a little bit. Let's open the trajectory and animate. No, the sum does not remain constant unless the trajectory is properly closing. Okay, as it is now. Let's go to the sixth and final one. There you go. And let's see. Let's go back to our first. So let's go ahead and see what happens here. Yeah. So for the sixth and final one, the ordering is A, D, C, B. We're getting this kind of an invariance here just for the sum and not for the product. And I will bet that if we tweak the caustic, that sum is not going to remain constant. Okay, sums have a harder time remaining constant if you're not in a proper closed N-gon, Poncelet N-gon. Okay, all right. So let's now do our final, next to final battery of investigations. Let's look at n equals 7. Okay. So we're going to go to n equals 7, and we're going to start with a very interesting n equals 7. It's the so-called, it's the self-intersected n equals 7 with turning number equal to 1. Okay? There's another n equals 7 where the turning number is equal to 2. I'm just going to go ahead and show you guys what that is. Here's another n equals 7 when you have 2 complete turns around the caustic. We're going to start with turning number equal to 1. This one over here. Okay? So P1, P2, all the way to P7, self-intersecting. And I'm going to define my diagonals in the following way. Okay, so let's go ahead and do I have A, B, C, D? I want to have A, B, C, D. Oops. Let's go back to A, B, C, D. A, B, C, D. Okay, so the diagonals for this n equals 7, turning number equal 1, are the following. P1 to P2, you can see here the dash red. Okay, P1 to P7, dash red, and the cross diagonal will be P4 to P5, or P5 to P4 if you prefer. And we have this labeling A, B, C, D. Let's look at what's happening to this family in terms of cross ratios. Okay, only the product is conserved. Let's go to the second ordering. Okay, both product and sum are conserved. So we got the sum of 5.48 and the product of 0.16 approximately for this particular ordering, A, B, D, C. Let's go for the third ordering. Now only product is conserved. Let's go to the fourth ordering. Both sum and product are conserved. Let's go to the fifth ordering. It looks like both sum and product are conserved. This number here is basically 3.13 times 10 to the minus 6, and it looks pretty stuck. So I would say this number is conserved. It's pretty small, but both sum and product of cross ratios are being conserved. Let's go to n equals 6. Again, both sum and product being conserved. So n equals 7, turning number 1 is very friendly. Let's go to turning number 2. Okay, turning number 2, and I'm going to define my my diagonals in the following way. I'm going to start from P1. I'm going to have a diagonal to P2, another one to P7, and my cross diagonal now is going to be P5, P4. Okay, and you can see here that my ordering, let's get the ordering that we like. A, B, C, D. Okay, so here's A, B, C, D. Now guys, I've swept under the rug the fact that on both n equals 7 cases, I have many more choices for my pre-diagonals. Okay, I'm just overviewing very quickly a few of them. Okay, the same is true here. Consider that if I choose these first two diagonals here, P1 to P2, P1 to P7, instead of choosing P4 to P5, I could have chosen, let's see, could I have chosen something else here? Oh, maybe I couldn't. Oh, looks like I don't have a lot of choices here, right? Oh, I do have another choice, right? I could have chosen P5 to P6 or P6 to P7. So I have three choices, right? So I chose as a cross diagonal here P4 to P5, but I have available to me, so I need a diagonal that will cut through these two lines here twice. Okay, so which lines cut through these lines here twice? And do not include vertices P1, P2, P7. They are P5, P6, P5, P4, which I just chose, and there's a third one, right? So which one is the other one? So there's this one, and there is, I thought there was a third one. Maybe there isn't. Maybe there are only two choices. So P3 to P4, and then I have P4 to P5, and I believe that's it. Okay, only two choices. But then I have more choices related to the choice of the original diagonals, right? I chose P1 to P2, P1 to P7. I could have chosen P1 to P6, P1 to P5, and then chose the other diagonals accordingly. You don't want to choose vertices that are right next to you because then you're not able to intersect them. But I could have chosen, for example, P1, P4, and P1, P5 as my first two diagonals emanating from P1. But let's just stick with these choices here, okay? And let's animate the family. Now, this was not a very happy thing to do here because I'm animating the caustic. Let's go back to the original family, okay? And let's animate the family, not the caustic. All right, so at this particular choice, A, B, C, D, I'm only managing to keep the product invariant. Let's go for a second choice. Now, for this choice, I have A, C, B, D, and only the product is invariant. Now I have A, C, B, D, only the product is invariant. Hang on, I don't think I changed that. I have A, D, B, C. Okay, A, D, B, C. Yes, for A, D, B, C, that's the second choice in my list over here. Both sum and product are invariant. So for the third one, we've already seen it. Let's say BCD1, only the product. The fourth one, again, both sum and product are invariant. For the choice ADCB, let's go for the fifth one. ABDC, let's see what happens. Both sum and product invariant. Nice. And then the last one, ACDB, what do you get? Both sum and product invariant. The caustic is shaking a little bit, but that's just an artifact of Mathematica. Ignore that. So our final example, let's go for n equals 8. We're going to go n equals 8, and stop, n equals 8. There's n equals 8. And for this particular case, I just chose the concentric axis aligned case. This is an n equals 8 family. Let's watch it. 8 vertices, very symmetric. There's some nice properties to it. There's some symmetries that is, when everything is axis symmetric like this, right? P1 and P5 are diametrically opposite. They are reflections with respect. So all proper opposing vertices are diametrically opposed to each other, or reflections of each other with respect to O. Okay, I could tweak this pair a little bit to make it be slightly non-concentric and slightly not tilted, but that's not germane to the video. I want to show you guys a couple of phenomena here. Let's go ahead and draw. And there's going to be many more choices of 3 diagonals here. Let's just show a couple of them. Okay, so here's the first choice. These 2 diagonals emanating from P1 and hitting P3 and P4. As my cross diagonal, I'm going to choose the line P2, P7. So here are my points A, B, C, D. Let's animate that and see what happens. My sum of cross ratios is constant. Let's do another 4-letter assignment. When I choose A, B, D, C, I get sum equals to 4 constant. Recall that for n equals 6, we had a choice that gave us sum equals to 6. Okay, so for n equals 8, we have a choice that gives us the sum of cross ratios equal to 4. The product is not constant under this lettering choice. Let's go to the third ACBD cross ratio ordering. And now we're getting a new miracle. Okay, both sum and product are constant, and the product is equal to 1. Okay, so let's try to be daring here. I'm going to open up this trajectory by tweaking the caustic a little bit. Let's tweak the caustic. I'm going to tweak the caustic. You can see here that the trajectory has opened up. And look at what happened. The product, even though this has been tweaked, remains equal to 1. But I've lost the constancy of my sum. Since this is no longer a proper Poncelet N-Periodic, but surprisingly, my product of cross ratios under the same definition that we were using before remains equal to 1. Okay, so this seems to be a property of 8 vertices, 8 Poncelet vertices in a trajectory, closed or not closed. Alright, but let's close it again. And when I close it again, I get both sum, more sensitive to closedness or not, and product invariant. Let's change the assignment, the lettering assignment, to the fourth configuration. Here's the fourth configuration. Now I have ACDB. Again, we're getting the same phenomenon. Both sum and product are conserved. Let's go to the fifth one. Only sum is being conserved, equals to 4. And let's go to the sixth one. Only sum is being conserved. Is this the end? Do I have more options here? Of course I do. Okay. If I go to n equals 8, there's going to be many more options. I have 1, 2, 3, 4, 5, 6, 7, 8 options here. Let's just look at a second one so you guys get a sense of what I'm talking about. When I choose it like this, okay, my choice of diagonals now has changed. My crossbow now used to be P2 to P7, is now P2 to P6. So I'm going to get different phenomena here. Let's look at a third choice. I can get this third choice where my cross diagonal now is going from P2 to P5. Again, I'm going to get different phenomena. Let's get a third choice here. This one, D. Okay, so again, I'm getting a different choice for the 2 lines emanating from P1. But I actually want to find one that is symmetric. Okay, and I think it's one of these. Let's see. That's still not it. Let's go to F. Let's get a symmetric one. Yes, this one Yeah, this is almost perfectly symmetric, right? So I have P1 going to P3. No, it's not, because I'm skipping one guy here and I'm skipping two there. I would like to skip two in each case, so let's see if I have one of those. No. Yeah, this one sort of is, right? Let's look at H. Maybe I didn't put it in the... Oh, yes, I did put it in the Pantheon. So let's just look at this one as a final example because it carries some symmetry with it. What do I mean by that? I'm actually connecting P1 to P3, which is just... Oh, it's not. I should have connected P1 to P7, right? Because I'm skipping one over here, and I should have skipped one over here. Okay? No, so this one doesn't have a lot of symmetry. Okay, well, we can still investigate it. So let's order it in the first way to see if it conserves anything. This one doesn't conserve either sum nor product. Let's change it to the second ordering. It only conserves sum. To the third ordering, it conserves product, which is a 10 to the minus 7 value here. Let's go to the fourth ordering. Also only conserves product, and now it's 10 to the sixth. Let's go to the fifth ordering. Now it's only conserving sum. And to the sixth ordering, conserving neither. Okay? So amidst these 8 or 9 odd choices of diagonals, and there's more than that, I should report how many possible choices of diagonals there are, you're going to get a lot of these phenomena. You're going to get, if you go back to the n equals 5 case, you're going to get cases where you conserve, so for one of the orderings on the n equals 5, for example, this ordering here, recall that we were conserving both sum and product. So as you move along to n equals 6, n equals 7, n equals 8, you're going to find certain choices of diagonals and labelings of the 4 cross-ratio vertices that will either conserve the sum of cross-ratios, a product of cross-ratios, both of them, or neither one of them. Okay? And the nature of this phenomenon is still not understood, and if you have any opinions, any ideas on what might be going on here, we'd really appreciate to hear from you. Okay, so thanks a lot for hearing me out, and this has been a longer video than I thought, but this phenomenon is quite rich, and I hope to see you in the next video. Thank you very much.